Okay. Now I still would like to see this in that bending, asymmetric stretching, symmetric stretching and so on. Okay. So the best way, I knew from the long method q1, q2, q3 are an independent variable here, right. That is why I worked out with q1, q2, q3, where q1, q2, q3 are this. This information came from the long method already. I will not have this information also in general, you agree? So, it is better to work not with some partial information from doing the mechanics explicitly, but to do it as if I am doing only group theory. We are going to do that. Is that clear? This q1, q2, q3 information I got because of my solving it as a method in mechanics. I do not want to do that. Okay. I want to do it as if I am doing a group theory problem which has 6 degrees of freedom in the xz plane. Fair enough? And then I want to see symmetric, asymmetric, stretching, everything in that language. Okay. So, that is the next step. So, I am going to get on to that step. To see these vibrational modes, is better to work with excursion coordinates. Excursion means displacement about its mean positions. Okay. I am going to choose this column or this row as the basis vector. What is this? Atom 1 x1 z1 followed by atom 2 x2 z2 followed by atom 3 capital X capital Z. How can I see this basis as a tensor product? Tell me. Can I see this as a tensor product? So, I am going to do something like this. Atom 1, 2 and 3, tensor product with X and Z. Okay. What is the meaning of this? If I write it in the long winding language, what is this? X, and this one I am going to put it as a subscript. Okay, x2, z2, x3, which is what I am calling it as capital X, and z3, which I am calling it as capital Z. Is that okay? So, now you see how tensor product gets in to looking at the basis state of displacements of all atoms is a 6-dimensional vector space, but that 6-dimensional vector space can be looked at as a tensor product of the number of atoms in a molecule, tensor product with each of their coordinates x and z, and this basis which I get can be viewed this way. Okay. So, now you can do the reducible representation, which will be a 6 cross 6 matrix for C2. What will that be? Not independent, no. It is a basis in the reducible basis in some sense. Okay. It is a 6-dimensional vector space the matrix representation which I am going to write will be a reducible matrix, and this vector space will also be reducible. Okay. In that sense it is, they are all, I can write a 6-dimensional basis here, and then I want to look at what are the irreducible bases associated with C2B symmetry. If you are looking at some higher groups, this could also be a valid basis, right. But for me I am looking at, like regular representation, I am looking at a nonlinear triatomic molecule which has 6 degrees of freedom. Let me write my matrices which is 6 cross 6 matrices, and from there I would like to do all those rules of, or the tools of character table, projectors, decomposition into irreducible representation, and fix which linear combination is actually the basis for the vibrational modes of your water molecule. Is that clear? Are you all with me? Some bit. I can see faces are. Is it okay? Math is okay, but physics part of mechanics, if you keep on remembering it, then you will appreciate what I am doing. Okay. I am doing this because I am assuming that I did not go through the long method of determining Q1, Q2, Q3. See, there the long method helped me to say that the vibrational mode should be some linear combination of Q1, Q2, Q3 only, but I am not doing that now. I am going to derive that from this higher vector space which is 6-dimensional vector space. 6-dimensional vector space is associated with the 6 degrees of freedom of this molecule. Okay, so how will you write the C2 element? So I can split this up into a 3 cross 3 of C2 and another 2 cross 2 of C2, right. It will act on 1, 2, 3. This will act on X, Z. Are you all with me? And I am doing C2 in the Z axis. So what will this matrix be? This is rotation by 180 degrees in the about the Z axis. So it will become, this will give you, this thing will give you minus X and Z. What about this? So let me also call what are the atoms. This is atom 1, atom 2 and atom 3. So what happens when you do about Z axis, axis as shown in this figure, 3 is untouched, 1 and 2 get exchanged. Clear? So what will that matrix be? This whole thing should give you 2, 1, 3. So what will be the matrix? So this acts on x1, z1, x2, z2, x and z, and this is what is the long winded thing, and I need to determine this. So let us write what is this. So this clearly tells me it is 0, 1, 1, 0. That is the matrix which will take, is that right? No, I will do it. Then 0, no, minus 1, 0, 0, 1. Yeah, thank you. Yeah. So now you multiply and write the 6 cross 6 matrix. The first is this, then you have a minus 1 0 0 1 0 0 okay. How have I generated the this is clear. I am using the tensor product power, okay. Using some kind of a permutation things here, subset of the symmetric group permutation elements. I am doing this tensor product to generate my matrix which acts on the complete 2n degrees of freedom for the triatomic nonlinear molecule. Okay. Okay. So, now getting back to the screen now. So, I have elaborated for you how we got this. I am calling this reducible one with the letter capital M. This is just to keep the nomenclature. That earlier one I called it as V, but it has nothing to do with, you can call whatever letter you want. Here I am following M. So, I have written this matrix and I have taught you how to write the 6 cross 6 matrix, right? Yeah. Capital X and capital Z is not quite invariant, X also changes to minus X under C2, okay. Which one? Will no, the larger molecule remains fixed, the X coordinate is going to get to minus X, Z will not change. So, there is some subtlety, let us go through this and then we will come back by a shortcut method which you are already getting onto in the next class, okay. So, there is another shortcut way of doing it, we will come to it. Once you appreciate this, then I can get to that other method, okay. Okay, are you all with me? Okay, so I have written this 6 cross 6 matrix, now you have to redo this for identity element is of course trivial, identity element trace will be, the character will be 6. Similarly, sigma v will also be 6 because it will both be almost the same. This character C2 turns out to be that these two are diagonal elements, they add up to be 0, clear. So, that is why I put the C2 character to be 0 for the reducible representation, and sigma v prime will also turn out to be 0, please check it, okay. Again do the decomposition of this reducible representation using the character table of C2v to find how many times which irreps appear, okay. So, that I will leave it to you as an exercise, okay. So, please try it out. Huh? Sigma v was different in Q1, Q2, Q3 basis, where I have removed the translation degrees and rotational degrees. Now, I am not doing anything, I am just taking the 6 degrees of freedom and I am finding out how the reducible representation which preserves the C2v symmetry breaks into irreps of C2v. Now, I have to remove the translation and rotation, which will do, okay. So, that is the additional work you have to do if I want to do this piece of work, okay. Anything else? Okay, so back to the character table of C2V, and gamma m, you can break it up and write 3 times A1 and 3 times B1, but as he already pointed it out, this is a 6 degree of freedom to start with, unlike the gamma V which involved 3 degrees of freedom. The 6 degrees of freedom, 3 of them belongs to the A1 irrep, 3 degrees of freedom, and 3 degrees of freedom will belong to the B1 irrep. But you have to remember it includes translation and the rotation, because I am doing it like a 2D plane. Okay, rotation about y axis, is that right? Rotation about y axis and translation in the xz plane. So, translation along x direction, if you look at this character table and this basis function, translation along the x direction is similar to the B1 irrep. Okay. Translation along z direction is like an A1 irrep. So, you can subtract the A1 and the B1, and rotation about y axis is also the Ry belongs to the B1 irrep. So, you will subtract additional B1 here, that is why I put a 2 times B1. These subtractions are to remove the translation degrees of freedom and rotation degrees of freedom. Okay. So, essentially if you subtract from 3A1 plus 3B1, the A1 and 2B1, you have to get back the answer which you got for, what did the answer come for gamma V? Gamma V was twice A1 plus B1, gamma M is thrice A1 plus thrice B1, thrice B1, yeah, and then this includes translation. So, A1 is for translation, okay. So, gamma m minus A1 minus B1, again another B1, this will be the, this will contain only the vibrational degrees of freedom, and I am claiming that this should be same as your gamma V. Can we check that? So, 3A1 plus 3B1 minus A1 minus 2B1 turns out to be 2A1 plus B1 . Okay. Still I do not know Q1, Q2, Q3. I can still say that whatever physics you did with Q1, Q2, Q3 essentially comes out after I subtract out the translation and rotation irreps out of the system. I am looking at only that, no, the molecule is in the xz plane. So, I am just doing only a 2D problem kind, right. Yeah. So, if I am looking at 6 degrees of freedom in a 2D system, 3 into 3 atoms into 2n, right, 6, and then you have to subtract out translation, which is 2, subtract out rotation, and you have to look at 2 into n minus 3 degrees of freedom, which are the vibrational degrees of freedom. I have not done the subtraction. So, whatever I am going to get out of this will have translations, rotations and vibrations. To look at the vibrations of atoms within the molecules without touching, without altering the center of mass of the system or rotating the system, you need to subtract those degrees of freedom. So, the irreps associated with the vibrational degrees of freedom, which you did from here mechanically, belongs to A1 twice and B1, but here it will be 3A1 and 3B1, but it includes translation and rotations. You have to remove the translation and rotation if you want to compare these two. Clear? Still I have not shown you the picture, how to get the Q1, Q2, Q3, that also we will do. Okay. Is this clear? Are you all getting some feel of how math speaks physics? Actually speaking what you want in the language of physics, we want to get those asymmetric symmetric modes, and we are going to see that now. Okay. Okay. So, I want you to take this reducible representation and find the projectors. Okay. I have given a projector for the A1, sorry, this should be 1/4 multiplying this, okay, it is not equal to. That 1/4 is because 4 is the order of the group. Okay. So basically this matrix I will leave you to check. Will you do it? Just have to take, I worked it out for you for the C2, you have to work out for all the elements, it is very simple, sigma V prime will be almost same, identity and sigma V are the identity operators. You just have to take the characters are all 1, you just have to sum up all these matrices. If you sum up all these matrices, you will end up getting a projector of such a matrix. I will leave it you to check this out, okay. And once you get this projector, you have to look at translation. What is the projector for translation? Suppose I am looking at translation along z direction, because A1, as I said, is associated with translation along z direction. The projector for conventional translation along z axis is just that you have to shift the z by some constant. I am normalizing the constant to be 1. Okay. So, this will be a projector. What do I mean by a projector? The square of this matrix should be itself. That is the definition of a projector. Am I right? So, this matrix which I have written is a projector for the translation along z direction, and translation along z direction belongs to A1. So, I am going to subtract from this matrix which I have generated the translation projector, which means one basis I have removed, one linear combination I have removed. Clear? Whatever remains, that matrix should be having rank 2, and you should be able to find 2 linearly independent bases for that rank 2 matrix. Okay. So, this I am saying is a rank 3, and then I subtract the translation, it becomes rank 2, should have 2 linearly independent bases. Okay. So, the 2 linearly independent bases in this basis, okay, you go and look it up, do it, and you will see that you get -1, 0, 1, others are 0. In the notation of this basis, I can equivalently write it as x2 minus x1, and that was nothing but your q2 up to an overall constant. q2 was x1 minus x2 is what I took. What I get is that, so this projector which I am doing, you can put an overall sign or overall factor. So, x1 minus x2 which I took as a basis turns out to be coming naturally from here, and again you can do the other basis for the A1, and that turns out to be, I get a -12 and a -12 and a 1. So, you can rewrite it as z minus z1 plus z2 by 2. So, basically it depends on the q. This z can be eliminated, but this is depending on the q3, right. So, I am just trying to give you a flavor that how, without even finding that q1, q2, q3 by long method, you can still work out the projectors and find the basis functions, and then you can say that the normal modes are these bases or linear combination of these bases. Once I have this x2 minus x1, I can draw the diagram which I showed you, this one. So, if x1, so you can resolve this component into x1 and z1. If x1 is going to in this direction, you can see that x2 is going in the same direction, right. So, this is one, and another one you can see is that the this is x2, x2 will be going in the negative direction and this one is going in the positive direction. So, you can net write it as x1 minus x2 and this one as x1 plus x2 and so on. Okay. So, I did not do the PB1, try that out, PB1 also. You should know how to write the corresponding projector for in the PB1 you have one X translation that you can subtract it out. You should also write the projector for rotation about y axis, subtract both of them from the PB and you should get one rank 1 matrix, and then that basis should give you x1 plus x2. Okay. Okay. Is that clear? So, I have shown you that q2 and q3 bases are obtained from PA1. I want you to see that q1 basis you will get it from PB1 after subtracting translation along x axis operator and rotation about y axis operator, which I have not done now. I want you to do it and check it out, and you should get the q1 coordinate from there. q1 is x1, that will be 1. So, basically in this notation it will be 1 0 1 0 0 0. This you should get when you are doing the. So, first of all write for the reducible representation which I called for the B1, which will be a 6 cross 6 matrix, which will involve summation over all the elements, character for B1 for every element and the 6 cross 6 matrix for every element. First write that out and then subtract translation mode along the x direction, which will be again a 6 cross 6 matrix, and then rotation about y axis in this basis should also be a projector. What is the definition of a projector? T squared, if you do twice, it should be same. That is the definition of a projector. So, please fix this and find what it is, that I will call it as P tilde B1 M, and if it operates on arbitrary state, I have to get this. I have not shown this, but you should try and check it out, and that will convince you that this is nothing but your Q1 in the earlier language, and you get Q1 basis to be the irrep belonging to B1. Q2 and Q3 are the basis which belongs to irrep of the other two A1. Is that right? So, just to summarize what we did today, so taking this atom, you are looking at the vibrational modes of these molecules. There could be vibrational modes which are symmetric, that is one possibility. Second possibility is, by this I mean there is a bond connecting them and then there is a relative motion between the atoms in the molecule without touching the center of mass of the molecule or doing a rotation to the molecule. Okay. So, this is one vibrational mode. If you try to resolve them, so this will go this way and this will go this way and this will be this way and this will be this way. So, you see that x1 is becoming, this is x2, right, in my notation. This was x1 and this one is minus x2. Okay. That is one, and this as a normal mode we write it as Q2, which is x1 minus x2. The other one is where you have a, this goes this way, this goes this way, right. The two atoms, the bond, it is an asymmetric stretching. So, if you try to resolve this, this is x2, z2, so you can see that x1 plus x2 is a good thing for this. Okay. And then what else? The other one is the bond change, which could be the other option, and that also should involve for you the way of writing it, you should see that. Okay. So, let me show the picture again, maybe now it will be visible in this language. You can resolve it and see what is happening here, what is happening here. These two are one and the same, no change, up to an overall sign does not matter. Similarly, these two stretching and shrinking in the same direction are one and the same, because it is going through a simple harmonic motion, right. These are the bending modes where this angle is reducing and this angle is increasing, that is also another simple harmonic motion, and you will see that two of them will be a linear combination of Q2 and Q3, one of them will be purely q1, which is x1 plus x2. Okay. I hope I have driven the point that you need character table, you need first to know the group symmetry of the molecule, character table, the basis functions, you need to know how to do the decomposition of a reducible representation in the basis which corresponds to 3n degrees of freedom for a molecule, and then you use projectors, remove translation projectors. To remove the translation projectors, you should also know which rep the translation belongs by looking at the basis states. Once you do that, you can fix all the normal modes by just doing those projectors, and you can draw those diagrams.